What's going on, guys? Welcome back to Musa Musa's YouTube channel, and we're back here with another video talking about integration using substitution. Okay, we'll be using the wonderful application of USub, which is my favorite thing to do when I'm integrating. Okay, let's get right into the video. So, for integration using substitution, we're going to take integrals, which sometimes might look kind of ugly, and use a neat substitution to be able to make the question a lot easier to deal with. So, for example, let's have this integral here. Let's say x, and then here we'll have square root of 1 minus, and let's do, who knows, I don't know, x squared dx. Okay. Maybe you can already tell me what to do because you know reverse chain rule. You will recognize that if I make this my function, if I consider this to be the function, I know that I need to have the derivative of this function present, which would be minus 2x. So then you chuck a minus 2 here, put a minus a half to cancel that off, and then you just apply the reverse chain rule formula, and you'd say this is going to be minus a half, and then it's 1 minus x squared. Because it was originally put to the power of a half, you would add on to the power and make it 3 on 2. And then you divide by 3 on 2. So you multiply by 2 over 3. And you put a plus c. And you'd end up with minus 1 on 3, 1 minus x squared to the power of 3 over 2 plus c. Okay? Fair enough. If you can do this, then just do this. You don't have to use usub. But I think using substitutions saves you a lot of time, particularly for harder questions. Show you what I mean. If we took this same integral, actually no, maybe this is going to disprove my point because this is going to take longer in this integral. But I will show you examples where it'll be a lifesaver. So let's say we have this same integral. How would the U substitution method work? Well, in extension 1, they're going to give you the U sub. They're going to say, let U equal 1 minus x squared. Okay. Really, we're doing reverse chain rule. Okay. But we're sort of spelling it out and we're working through it methodically instead of just sort of saying, oh yeah, I know there's this rule. I'm going to add 1 to the power, divide by a new power, and the f dash x just disappears. Okay. We're sort of doing it more methodically. And I guess when the questions do get a bit more difficult, there's like less room for error when you're doing it this methodically. Okay. Who knows? But they say let U equal this. So we've saved ourselves some, we don't have to consider it ourselves. What we're going to do, this is sort of the aim, to take everything in my integral, which has x's and dx's, anything that's in terms of x, and replace it all with u's. So replace the dx somehow with du, and all the x's there with u's. Okay? So let's have a go. Well, if u equals 1 minus x squared, we now have a replacement for this. Let's find the replacement for dx. So what I'm going to do is take the derivative of both sides with respect to x. So my left-hand side is going to be du on dx equals, and my right-hand side is going to be minus 2x. That means du equals minus 2x dx. I know it's not really a fraction, but let's just treat it as such. Okay. I got kicked out of the last class. Some lecturer walked in and she needed to use the room, so I left. But let's just continue. So that's how I got the du equals minus 2x dx. Now it seems like in order to get a du, I need to replace a minus 2x dx with it. But I only have an x dx. So it seems like I should be putting a minus 2 there and then putting a minus a half there. Now, this minus 2x dx comes to give you the du. And in one line, we replace it all. We don't do sort of like replace some and replace the other later on, all at once. That shaded blue all goes to du. And then it becomes the square root of 1 minus x squared is u. So the square root of u.
This is going to be minus a half square root of this thingy here. And now it's just like normal integration, like normal power rule. You just add 1 to the power, divide by the new power. It basically eliminates the need for reverse chain rule. So to the power of 3 over 2, multiply by 2 on 3 plus c, and we get minus 1 on 3, u to the 3 on 2 plus c. Now, because the original question came with x's, we have to go back to the original variable. So now let's say, okay, well, u was used and it was very necessary to help us integrate, but we have to go back to the x's. It's kind of like a catalyst in chemistry, right? It shows up in the beginning just to incite a particular reaction, and then it comes out in the products in the very end, right? So it sort of just helps the reaction take place, but it doesn't affect the final products. Nice. So that's that. Of course, you can get given questions which are definite. Okay, so they don't have to be indefinite ones. You can even get ones, for example, that are like, let's say, the integral from 0 to 1 of x squared, x cubed plus 1. And we'll put this to the power of 4 dx. Of course, you can probably do this using reverse chain rule. I'm sort of still giving easy ones, but it's okay. So let's have a go. Integrating this, and then I need to give you the substitution. Let u equal x cubed plus 1. So du on dx will equal 3x squared. So you're always taking the derivative to replace the dx, multiplying both sides by dx. We get du equals 3x squared dx. Now, I don't have a 3, so I'm going to chuck in a 3 and then put a third. Now, all of this 3x squared dx just becomes the du. I have a replacement for this x cubed plus 1. It's just u, but I need to replace these limits. So this is the extra thing you've got to keep in mind for definite integrals. You have to change the x limits into u limits. So we're going to set up a little table. We're going to say this is an x, this is u, and we're going to chuck in our u limits. So 0 and 1. And what am I trying to say? Oh yeah, when x equals 0, u equals 1, and when x equals 1, u equals 2. So you're basically just subbing it into this to find the u limits. So now your integral can be written as a third. The integral from 1 to 2 du, and then it's u to the 4. So it even makes substitution easier. Put that there. This is a fifth of u to the 5. And then it's 2 to the power of 5, which is 32 on 5 minus 1 on 5. So it's 31 on 15. Perfect, perfect, perfect. Okay, so that's how you do this. I'm going to give you an example, or I'm going to give you a few examples, and I just want you to have a go. So let's do the first one. I guess I don't know how easy I should make these. The beginning, at least. I know we did this question in another video, but I want you to have a go here. So I'm giving you the U sub. Give you a few. So I'll call this A, call this B. Let's have a go at, I'll give you a definite one. X times the square root of 4 minus X. And this is going to be from minus 5 to 3. You can probably pick out why I'm letting whatever I am letting equal U. It's because that's the part that's creating the chain rule. That sort of corresponds with the f of x in the reverse chain rule formula. Okay, that's effectively the premise behind why we're doing what we're doing here. Okay, and I'll give you another one here. So let's say should I make this with limits? Yeah, 1 to 2, and we'll say u equals 4 minus x squared. All right, have a go at these ones. Unpause. So for the first one, A, we're going to let u equal 1 minus cos x. So let's take that down to here. If that's that, we can find du dx. The derivative of 1 minus cos x is going to be positive sine x. Multiplying this side by both sides by dx. We're going to get du equals sine x dx. Seems like we have a replacement for this sine x dx. And we have a replacement for the 1 minus cos x. So this integral now becomes the integral of the root of u du. That's u to the half. Adding 1 to the power, it's going to become 3 over 2. Dividing by the new power, it's 2 over 3. There you go. Not bad. Part B. Question B, rather. Copy. Copy. Letting u equal 4 minus x, that means du on dx equals, we've got to differentiate the right-hand side with respect to x, that's minus 1. That means that du equals minus dx by having multiplied this side by dx and this side by dx. Because this is a definite integral, we also have to change the x limits to u limits. So let's create a little bit of a table here. And subbing in minus 5 and 3, when x equals minus 5, 4 minus minus 5 is 9. And then when x equals 3, 4 minus 1 is 4 minus 3 is 1. So then we're going to write this out as, do we have a replacement for everything? I think we do, actually. So we have a replacement for this 4 minus x. I guess we have a replacement for, let's even write this a bit differently. We could even write that as dx equals negative du. So we found a replacement for dx. It's negative du. We have a replacement for the limits. This x, all we've got to do for that is just rearrange this equation. So if you rearrange this, we get x equals 4 minus u. Okay? Perfect, perfect. So now our integral goes from 9 to 1. X is going to get replaced with 4 minus u. And then that's going to get replaced with u being square rooted. And then the dx is getting replaced with negative du. So I'm just going to put the du here and then put a negative, I guess, at the front. You might ask, how do I know the 9 goes at the bottom and the 1 goes at the top? Isn't it usually you have the lower number at the bottom and the high number at the top? Yeah, you're effectively right. We, by convention, like to write the lower number as the lower bound. But there's nothing that's stopping us from doing it this way. How do I know which one goes where? Because the minus 5 corresponds with the 9, and the minus 5 was at the bottom, the 9 has to go at the bottom. The 3 was at the top, and the 3 corresponds with the u value of 1. That means the 1's got to go on top. If you're not super convinced with this sort of method, by having it written as a 9 there and then a 1 there, you can recognize the fact that if you take negative of an integral, of a definite integral, you can swap the bounds. So you can now just make this the integral from 1 to 9. And that's a way of applying the negative. Okay? And that's why it works out, because the only time where the lower bound and the upper bound become like the other way around, as in the higher one is the lower and the upper is the smaller one, is if the derivative or the dx is going to get replaced with a negative. So there's an extra negative. So then this is going to be this. Let's write this as u to the half, and let's expand this. So it's going to become 4u to the half minus u times u to the half is u to the 3 on 2 du. Now it's just time to integrate. So integrating this, it's going to be 3 on 2, 4 times, and then we've got to by 2 on 3 because we're dividing by the 3 on 2. The minus, and this is u to the 5 on 2, but then we're dividing by 5 on 2, so it's going to be 2 on 5. This is 1 to 9. So subbing in, you have 8 over 3, 9, 3 on 2, minus 2 on 5, 9 to the power of 5 on 2, minus, and then it's 8 on 3. I guess 1 to the power of anything is just 1, then minus 2 on 5. Okay. Let's see how good our mental math skills are here. Square root of 9 is 3, 3 to the 3, but then you're dividing by 3, so 9, so then it becomes 72 minus 3 to the power of 5 is 243. 243 times 2 is 486, so minus 486 on 5, then minus 8 on 3, plus 2 on 5. Okay, I should probably use a calculator for this. There we go. I guess we get this number. We get minus 412 on 15. And that should be correct. I feel like I could have done that in my head. It is what it is. Alrighty. Now, definite integrals, you can do it this way. Another way of doing it is to get rid of the definite altogether. Solve it as if it's an indefinite one. So just the integral, solve it for just the indefinite. Go back to the original x. So at the end, when you get this u business, go back to your x variable, and then go and sub in your x limits. But I feel like that's such an extra effort. So there's no point in ever doing this. Okay. Alrighty. Part C. So du on dx equals minus 2x. That means du equals minus 2x dx. That means I need a negative 2. Oops, I need a negative. I already have the 2x dx, so I just need a negative. I'll put a negative there. X and u limits. So 1 and 2. When x equals 1, 4 minus 1 squared is 3. When x equals 2, 4 minus 2 squared is 0. So this becomes negative the integral from 3 to 0 of this whole minus 2x dx just becomes du, and it becomes 1 over the square root of u. Nice. So then I'm going to apply this negative just so I don't, a lot of times you'll forget the number on the the very end. So if you want to apply it, that's a good way of making sure that you're not going to forget it at the very end. So let's apply it and say 0 to 3, u to the negative a half. Adding 1 to the power becomes u to the power of a half. Dividing by a half is 2, 0 to 3. So then it's going to be 2 root 3. Nice. And then question D. All right, so letting u equal e to the 2x, that means du on dx equals 2e to the 2x. That means du equals 2e to the 2x dx. I need a 2 here because that's going to replace this all with du, and that's that's this, and this is going to become the du. So now my integral becomes cos of u du, which becomes sine of u plus c, which is sine of e to the 2x. Whoa, whoa, whoa. Oh, ho, 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 ho. Did I just forget to put a half out the front? Bruh. There you go. My bad. I put the 2 there. Forgot to put the half. Okay. So that's how you do these sorts of u subs. I feel like with more practice, they become a lot easier. Okay. But yeah, this is still sort of basic u substitution. Okay. Because now we're going to be dealing with a bit more interesting u subs, where instead of like having u as a function of x, we're going to have x as a function of u. Okay. Here's an example. The integral of, we'll say 0 to 1. Okay. Oops. Let's make that just that. And we're going to say let x equal 1 minus u squared. The process is still very similar. It's just that you may need to differentiate a bit differently. I don't know. Have a go. Try and replace everything, and then come back to me. Alrighty. Now that you've had a go, let's do this. So instead of taking the derivative with respect to x, I'm going to take the derivative with respect to u. So I'm going to take d du, d du. So this is going to be dx on du equals, and I'm going to differentiate my right-hand side with respect to u. That's minus 2u. I'm going to multiply both sides by du. And you get dx equals minus 2u du. Oh, forgotten that. Okay. Perfect. Now I have a replacement for this dx. It's just going to be this minus 2u to bro. Yeah, get the idea. I have a replacement for this x. It's 1 minus u squared. And all I need to do to replace, and I guess I can also replace this inside x with 1 minus u squared as well. I just need to replace my limits with u limits. So u squared equals 1 minus x. I'm just rearranging this first thing here. And let's go to x and u limits. So 0 and 1. Alrighty. When x equals 0, u squared equals 1, taking the square root, we're going to have, so we're going to have u equals plus or minus 1. How do we deal with the plus or the minus? Okay. That's a very good question. We're going to take the positive, and I'll explain it in a moment. Okay. So let's just like that. Let's take the positive. So that's going to be 1. And then when x equals 1, this is going to be 0. So my integral is now going to be 1 to 0. The x is, where is the x? 1 minus u squared. It's the square root of 1 minus u squared. And then the dx is going to get replaced with minus 2u du. Okay. So let's just clean this up, particularly clean up the inside. This negative 2, we can take it out. In fact, this negative, I'm just going to use to swap these and make that 0 and 1. It's going to be 2, 0 to 1, 1 minus u squared times. And then this is going to be 1 minus 1 plus u squared. And then we're going to be taking the square root of u squared. So I'm going to write that in here, actually. Times u du. Now, this is why I am taking the positive square root. Do you see how my original question came like this? The square root of 1 minus x. Another substitution you could have used is you could have said, let u equal to the square root of 1 minus x. That's sort of the same substitution as we've done here, okay? But we're given it in a different form. The fact that this is a positive square root is supposed to sort of suggest to us that we should be taking the positive values. I know it's sort of annoying, but yeah, that's kind of the method that you need to take. If you take the negative square root, then here, when you take the square root of u squared, you should then go and put an extra negative. Okay. I know it sucks, but that's effectively the reasoning. So just take the positive square root. Anyway, this is 1 minus u squared. This is just going to be u times u is u squared to u. Now we'll just expand this. And now we can easily evaluate. So 2, 1 on 3, u to the 3, minus 1 on 5, u to the 5, 0 to 1. This is going to be 2, a third minus a fifth. This is going to be 2 on 15, 4 on 15. Okay. So take the positive square root because we had a positive square root present in the original question. Granted, they've given us a substitution which I probably wouldn't have used. But anyway. I guess let's have a go at this one now. 3 root 2 to 6 of the square root of 36 minus x squared. And we're going to be using this substitution 6 sine u. Have a go. Pause and then unpause. So we need to replace everything. It seems like we have a replacement for this x. We need to replace this dx. So instead of taking d dx, I'm going to take d du. So it's going to be dx on du equals 6 cos u. That means that dx is going to equal 6 cos u du. My limits, this is where I've got to, whoopsie. This is where I have to rearrange this. Because I'm subbing in x values and I'm getting u values, I have to rearrange this and get x on 6 equals sine u, and then u equals inverse sine of x on 6. 3 root 2, 6. When x equals 3 root 2, 3 root 2 on 6 is root 2 on 2, which is the same as 1 on root 2. And when does inverse sine, or when does sine give you 1 on root 2? Pi on 4. And then when x equals 6, sine inverse of 1 is pi on 2. Remember, you have to be using your domain of the inverse sine function, which is from minus pi on 2 to pi on 2. So you can't be giving me like, oh, it's also 1 over root 2 in the second quadrant, which is 3 pi on 4. No. Only in the first and fourth, because that's the domain of the inverse, or the range of the inverse sine function. I feel like we have a replacement for everything now. So let's go to this. Pi on 4 to pi on 2 of the square root of 36 minus x squared is going to be 36 sine squared u times dx, which is 6 cos u du. Okay. Pi on 4, pi on 2. If we factor out a 36, it's going to be the square root of 36, which is 6. 6 times 6, 36. So let's put that out the front. And then it's going to be the square root of 1 minus sine squared. Well, 1 minus sine squared cos squared. Square root of cos squared is cos u. So it's going to be cos u from here times cos u, so cos squared u. du. And then we have to go and use our replacement for cos squared. The replacement is cos squared u is going to equal a half of 1 plus cos 2u. So it's going to be a half of pi on 4 to pi on 2, 1 plus cos 2u. This is going to be 18u plus a half of sine u, sine, whoopsie, 2u. Let's write this out a bit better. From pi on 4 to pi on 2. And let's sub in pi on 2 plus a half of sine pi is 0, then minus pi on 4 plus a half of sine pi on 2. So plus a half. 18 pi on 2 minus pi on 4 is pi on 4 minus a half, and then multiply by 18. Nice. So then this is going to be 9 pi over 2 minus 9. Very good, very good. Well, I forgot my equal signs for everything. Okay, that's the premise. It's just the fact that you have to differentiate with respect to u, and then we're going to replace the x with something, all in terms of u's. Okay, have a go. And I think that's the end of extension 1 integration. So yeah, goodbye.